Hi, so this is a summary of today's lecture, where I just quickly want to recap the notes and emphasize the main messages. We talked about a reminder of uh, special relativity, where we even went a step further back and talked about rotations in usual Euclidean space and discussed the notion of a vector, basically an arrow in space, in the normal three-dimensional space. And what makes it mathematically a vector is that it transforms like a vector. If you apply a matrix to it, you have a transformation. And if the matrix has a particular form that uh, the product of its transposed with itself gives 1, so that it's transposed is its inverse, and that its determinant is 1, means that it on the one hand preserves angles and on the other hand length. And we can see that this kind of multiplication preserves also the scalar product of this vector with other vectors and with itself, obviously. So if you multiply two vectors to get the scalar product, we can check what happens if we multiply two transformed vectors. Yeah, we just write them as a matrix multiplication. Then we apply the transposed signature to this vector, and you know how to apply transpose to composite multiplication of matrices. You reverse the order, and then you get the RT on the other hand on the other side of the vector, and then you have RT times R that gives you 1 by definition of this orthogonality definition of the matrix. And then you see that once this is dropped, we just have the normal scalar product between x and y, which just means that whatever happens when you rotate a vector, its length doesn't change. In other words, in physics, it means if you look at the vector in different coordinate frames where you rotate them or move them around, you still have the same vector which represents the same physical reality. Now, the next step to go to special relativity means that we have vectors in 4 space where we have x and t, and we do 4 sums here. So as we discussed also yesterday, we have the summation over repeating indices, and here we have the metric, as I said, because we have a covariant and contravariant vector. When we multiply them, we get here the time components, or the zero components minus the spatial components, right? And this norm has to be preserved. This is a new norm with this new metric on this Lorentz space, and it has to be preserved. So just to compare those two, we could have look at different transformations. We could look at Lorentz transformations or rotations in 3-dimensional space or in 4-dimensional space-time. The invariance would be, for the Lorentz transformations, the scalar products 4 vectors. For the rotations, it would be the scalar products of ordinary vectors. The spaces are called Minkowskian or Minkowski space or Euclidean space, going back to the mathematician Euclid. And also the metric that acts on those spaces is the Minkowski metric, or just the Kronecker delta, or the Euclidean metric, where here this is just a simple diagonal matrix with 3 entries on the 3 ones on the diagonal. Here we can repeat how to do the summation or the scalar products of these 4 vectors. We multiply x and y as a covariant and contravariant vector by raising the index of y. If we started with a covariant vector, we would raise the index of y to be a contravariant vector to contract it with this index of x. So we have to insert this metric eta. We know the form of eta, and we know how to perform the multiplication. Now, what does it mean physically? we understand, or we really need this norm to be preserved because it has a distinct physical meaning. In particular, if we look just at two-dimensional space, here we have time and x is just one coordinate here. This represents the space now. We have a vector s and the vector v. So we have the norm, the Minkowski norm of S is the time component squared minus the space component squared. And we see that the time component of S is larger than the space component of X, so the norm is positive. The vector is called time-like. And that also means that the it represents a configuration that is where that is causally connected. So in principle, it's possible to go from this point to that point in by having a certain velocity. We go from this point to that point having the velocity t. Having the velocity v that is smaller than the velocity of light, and we reach this point here. On the other hand, if we have a vector where the spatial coordinate is larger than the temporal coordinate in this diagram, where the defining property of the diagram is the speed of light, we see that the norm becomes negative, right? So the time component squared minus the time component squared minus the space component squared is negative. And this is a space-like vector. So in order to go from this point to that point in space, we would have the interval in time is so small that we would have to move faster than light. This is not possible. So those points are not causally connected. They cannot exchange information. And those can here on the other side. And the dividing line is this light-like curved line where to go from that point to that point or to that point, one would have to move with the velocity with the speed of light. So the norm the norm contains physical information, and in particular the sign of the norm tells us whether events are causally connected. So if you have we have a positive norm, we have time-like vectors. Negative norm, we have space-like vectors, no causal connection. If the norm is zero, exactly zero, that means that only the light can actually move between those space-time points. Now, as a note on the notation of vectors here, we see that a derivative, we can take a derivative with respect to a 4 vector, and the derivative of a contravariant derivative with a raised index corresponds to a derivative of a function with respect to a covariant vector with a lower index. And then explicitly written coordinates, there's derivative with respect to t, and the derivative with respect to the spatial coordinates has a minus. And when we have a covariant derivative, it's a derivative with respect to a contravariant vector, and there's no minus sign here in the spatial derivatives. That means applying, for example, that a derivative with respect to mu to the vector nu gives us a Kronecker delta. We can work this out because it's just taking the time derivative of the time component, which gives you 1. Then we take the we can take the spatial derivative with respect to the spatial indices, and then if those indices are both matched to be I and I, that would also give you 1s. Otherwise, if you take the time derivative with respect to the spatial coordinate with respect to time derivative, take a time derivative of the spatial coordinate, that would give you 0. So that's why this contraction gives you actually Kronecker delta. Similarly, you get a Kronecker delta as well with a different combination of upper and lower indices, but still it's a Kronecker delta because it is a diagonal matrix, essentially, just in a transposed representation, because if you take a derivative of time with respect to time, that gives you 1, otherwise you get zeros and so forth. And we have talked about the definition of the Kronecker delta as well. Now we briefly mentioned what was the contraction of these two metric tensors, eta mu nu and eta mu nu, and that gives you, as we said, the diagonal matrix. And then also this, the diagonal matrix is also summed over its diagonal entries, because we have all the indices contracted and we have to have just a number. So summing the diagonal matrix over the diagonal over the diagonal gives you 4 times the 1, which is just 4. Now, if we have this scalar product we already discussed, x times y, in Minkowski space is done by an insertion of the metric tensor, and we can define the Lorentz transformation, right? A boost or like or a rotation in this 4-dimensional space-time as acting on a vector by a 4x4 matrix, and it gives you another vector x prime. Now the defining quantity of this matrix has to be that it preserves the norm, as in the case of the Euclidean space. It should not change the product, because we said the product, the norm of the vector, defined is a physical observable and has something to do with causality and so on. It cannot be changed by changing of reference frames. So we do this product and we see what happens with the primed coordinates here. So we rewrite first. So first we define this scalar product as we know it, and then we write down the definition of the Lorentz transformation from above for both x prime and y prime, to have this express them as x and y with a lambda, big capital lambda here, denoting the both Lorentz transformations. Now we know that this has to be equal to x, y without the primes contracted with the metric tensor, because this is the scalar product on the Minkowski space in the other frame. Yeah? And those have to be equal. And then just comparing the sides of the equation shows us that this here on this side has to be equal just to this metric tensor alpha beta, because it cannot be anything else in order for this equation to hold. Yeah? So this is the defining equation in index notation, and we can write it in matrix notation by just seeing that this is the transposed matrix multiplying the metric tensor from one side, and the normal non-transposed matrix multiplying the metric tensor from the other side just gives you back the metric tensor. So this is the principal equation that defines the Lorentz transformation. We could also check, essentially by analogy, that the scalar product of p times p of the four momenta, which carries the energy and the spatial momentum in the spatial coordinates, is left invariant by Lorentz transformations, because it is also a 4-vector. And we have constructed the Lorentz transformation such that it leaves this Lorentz vectors invariant. And it has to be this way because the mass is a physical quantity, so it cannot depend on the frame. So it has to be an invariant. Then we also define a special subgroup of those Lorentz transformations that we have defined just by this equation here, as the ones that have the determinant equal to 1. That is called proper. Yeah? So they don't also change the length of the vectors, so we call it proper. And they are 0, 0, so their temporal component is larger or equal to 1. And this is called the orthochronous part of the Lorentz group. Orthochronous means that it preserves the time direction, from Greek ortho, the right or straight, and chronos, time. Well, we can also do the following and expand the Lorentz transformation as a matrix by having the diagonal matrix plus a small deviation from this diagonal matrix. Yeah, so we generally can do that as we can actually prove that the proper autochronous Lorentz group, which is in physics typically called just Lorentz group, is a real group. Yeah, not yeah. It has the properties of a group, so it means that we can generate its elements starting from the unit element and adding a small parameter and successively adding this additional parameters because those objects are called the generators of the group. Yeah, so this is a part of group theory. So once we have identified the properties of this structure as a group, we can use this expansion to define a generator and then continuously deviate from the unit matrix to construct any Lorentz transformation we want. So we can take again the defining equation for lambda to find the properties of omega, the generator, plug in here this expansion, right? Then we can compute what we get from this bracket, and then we see that this has to be equal to that. So we know that this part here has to vanish, which just means that omega transposed has to be equal to negative omega. Yeah, so when we that in coordinate in an index notation means that if we flip the indices of this omega, we get a minus sign. Yeah, so it's like transposed, it's equal to its negative. So it's called it's antisymmetric. Good. So we have now found the properties of the generators of the Lorentz group, and now it works. And we will look a little bit also on its properties in the exercise sheet. Now coming to the notion of classical field theory, we discussed a little bit on Monday, and we did this derivation for continuous fields today. So the action is defined in such a way that we have a Lagrangian, the integral over time over a Lagrangian function. However, in field theory, Lagrangian function is actually a Lagrange density of a field, where the field is a continuous function on the space-time, and instead of a derivative of derivative of the position, as we had before in classical mechanics, it's not a q dot. So four derivatives of the field are also the things on which the Lagrangian depends. Then the Lagrangian density is integrated over the whole space, and since we also have the integration over time, we integrate the Lagrangian space-time density over the entire space-time. Yeah, so overall, this matches. So this is a space-time integral, and this is a space-time density. Now, we want also to apply the principle of maximal laziness, the least action principle. So we apply this variation of the action. And it really goes by chain rule. Yeah? So we do the dl d phi d phi, where this is in principle just pulling through this variation in phi and applying the chain rule to L. And also the same applies to the variation with the derivatives of phi, dl d mu phi, derivative of L with respect to d mu phi times the variation in d mu phi. Now what we have to do is to apply partial integration. Yeah? So we have actually here the space-time integral, and we can, by the rule of partial integration, notice we notice essentially that we have sorry, let me just start over. We need to get those functions here in the same form. Yeah, so we want to bring this derivative over to that function. Yeah, so we take this integration here and we perform a partial integration where this derivative goes over on that function. We flip the sign, we get a minus sign from this partial integration, and we get the boundary term. So the boundary term is here. So we get a total derivative that acts on this term and the variation with respect to phi. Yeah. And what we wanted, we have collected the terms that are proportional to the variation of phi here, and that are non-zero everywhere in the space. But this boundary term, we know that the integral over the total derivative over a space is equal to the surface integral over this function. We will remove the derivative and replace the volume integral by the surface integral over the boundary region. This is the surface integral theorem, and this is equal to 0 because we assume that all the variations vanish at the boundary. This is a assumption that's always made also in classical mechanics. We assume that variations vanish at the time, initial and final time, and here we have to assume that variations vanish on the boundary of the integral. And this doesn't really, we don't really lose generality because we can make our boundary arbitrarily far away and it will not ever affect us by the principle of locality. So it doesn't really matter, but we still assume this. Now what we are left with is just this bracket here, because we know that the variation doesn't vanish in the bulk of the space here. We know that this bracket has to vanish, and it gives us this, which looks very similar to the equations of motion for classical mechanics, but now we have the derivatives with respect to fields and with respect to space-time derivatives of fields. And we have a summation here over this index mu that runs from 0 to 3. Good. Now, after that, we discussed the so-called Klein-Gordon field. Yeah? This is the first and simplest field theory that was written down. And we see here that it has actually a lot of analogy to the harmonic oscillator. If I may remind you, here in the harmonic oscillator, we had q dot and q dot here. So we here essentially have derivatives of phi multiplying each other. We have a square of derivatives, and we have a negative phi squared term, and it's quite similar to the negative q squared term. So there is some similarity to that. Anyway, we come to that to the interpretation in a second. What is important that is that it is a Lorentz scalar. Lorentz scalar because the phi is essentially just a value of the coordinate x somewhere in space-time. If we apply the Lorentz transformation, we can't really apply it to the phi itself because it's just a point. It doesn't transform at all. It stays the same. But so the value doesn't transform, but we can apply, and we have to apply the Lorentz transformation to the to its argument, to x. So if we have phi of x prime, so phi prime, the transformed phi field, is just the phi of the transformed coordinate, and we know how to transform coordinates by multiplying with the Lorentz transformation. So this is the transformation property of the Lorentz scalar, and this Klein-Gordon field equations are invariant under this transformation. Now we can use our equations of motion from before. Here we know that first we have to compute this dl derivative of L with respect to derivatives of the with respect to derivatives of the fields of phi. So we here explicitly write d mu alpha d alpha phi d beta phi, the contraction with respect to the metric the Minkowski metric with alpha and beta, and we take the derivative of this with respect to d mu phi, and that term has to be also contracted here with the outer derivative. But let's first focus on this term. So we get first terms that go like d alpha, where d alpha phi is left untouched. We basically do the product rule here of derivatives. And when we derive d beta phi with respect to d mu phi, we get only once when betas and mu's match. So we get a canonical delta b mu. And otherwise, if they don't match, this is just zero. And you just have a binary answer. Either you have the same function, you derive it with respect to itself, then you get a 1. If you have different functions, you get 0. So you get this term from that part, and from that part you get, so this remains the same, and then you take derivatives of d alpha phi with respect to d mu phi, and you get this other Kronecker delta. Then we are left with this eta alpha beta here in front, and have to do the contraction with respect to the outer external derivative mu here. Well, we just noticed that by combining the indices, we get actually twice the same. Here we take a derivative of the field and contract it with the extra index mu on the outside here, because this Kronecker delta tells us that mu is the same, or beta is the same as mu, so we can take mu to be here, and this alpha is contracted over, so we actually contract the indices here to combine those two derivatives together into the four-dimensional version of a Laplacian operator, but never mind. It's just a contraction of the all the indices between two derivatives, very similar to a second derivative. Here we have the same game with the indices, but since we have twice the same term and the factor 1/2 up in front, we just get these two derivatives. Basically second derivative hitting phi. The second term here, we have to take a derivative with respect to phi of the Lagrangian. It's even simpler, so we get minus m squared phi squared, taking derivative with respect to phi. We get twice m squared phi, and it's, the minus signs cancel and the twos cancel, so we get m squared phi in general. So we are left with is the second derivative of phi plus m squared phi equals to 0. It's actually interesting if we look and remember the quantization prescriptions, where we have taken the momentum and energy operators to just be derivatives. This is to make connection to quantum mechanics, and we will discuss this in more detail later. But here, if we make the connection to quantum mechanics, we just see that this equation where we have the e squared minus p squared coming from this bit, from this minus dt squared plus grad squared acting on phi, is the same essentially as having e squared minus p squared, and we have the m squared bit here. So rewriting this equation in this way would be, or is actually what you would have guessed if you would try to take the relativistic equation of Einstein and just naively plug in the definitions of the quantization the prescription for quantization, replacing p with the derivative with respect to space and e with the derivative with respect to time. Then you would get exactly this relativistic equation, which is the Klein-Gordon equation. And this is also what people started with at the beginning, before they introduced the multi-particle notation and so on. So there were the first attempts to quantize a relativistic system were done by this equation, and there people actually noticed that they are running into inconsistencies when they just look at a single particle and formalism. But we will come to that later. Anyway, moving on, we have here as well the canonical momenta, or in analogy to the classical mechanics, the canonical momenta are defined by the derivatives of the Lagrangian um, density with respect to the time derivatives of the fields. And the Hamilton is analogously defined by the time derivative of the field multiplying the canonical momentum, subtracting the Lagrangian. So doing this exercise with the Glenn-Gordon equation up here, we can convince ourselves that we get this equation here. We did it on the whiteboard. And we can now also interpret this equation. We know that this is, this is just the kinetic energy of the motion, because of the square of the canonical momentum, and this is the kinetic energy of the formation. And here we have a potential energy analogon of that goes as the m squared of the particles. So it's the total energy cost or energy budget of having any particles of this type at all around. So this is the total energy of the system. As we said, the Hamilton function has to be that, and it indeed is. Finally, coming to the solutions of the Glenn-Gordon equation, they are a simple way to generate solutions by plugging in the plane wave solution ansatz. Yeah? So it's just the e to the I kx, where k and x, x is the space coordinate and k is the momentum vector, basically, or the wave vector, better to say. And here again, double index summation is assumed we sum over space-time indices. So there are 4 components in this sum here. And we have like a times e to the minus ikx plus b star e to the plus ikx. We want the solutions to be real for now, because we are looking at the real quantum field. And we are now we can just check explicitly what's happening. Take the derivative of phi and get 1 power of k down here, also with the appropriate i's. The second derivative of phi gives us a second k down here. They multiply well into this k squared, and we see that combining this just gives us minus k squared phi. That is good. So this is good news. We now just have to identify k squared and m squared, and we're done. We understand that k squared has to be m squared, but the only vector we know that actually squares to m squared is the p vector, momentum vector. So we know the general solution has to go as e to the minus ipx plus, and the other coefficient a star e to the plus ipx, yeah, where we have also used that b star has to be equal to a. And now we have this full solution where we have to integrate, because we found that the solution for each momentum, we integrate it over all possible momenta. So we sum all possible momenta as we have found the solution for one momentum, and have the general solution for x. Here, this factor of 2, 1 divided by square root 2 EP, where EP is the energy of the particle with momentum p, is introduced for later convenience, and we will also discuss why that is good. But for now, the important thing is we have essentially the composition of the general solution by summing up all possible special solutions that we found here by this ansatz. Okay, finally coming to the last bit of this topic, we have looked at conservation laws and symmetries.